Okay. 13.1, we learned what a space curve was, we learned what a vector function was, and how to draw the curve, right? 13.2, we learned about the tangent vector, and we learned how to integrate vector functions. Okay? What we're going to do today is we're going to use a little bit of everything. So I want to quickly review how we found arc length in Calc 2. To show you how we're going to do it in Calc 3 for space curve. And the theme of today is all about understanding motion on a space curve. So that, for example, if there's a bird taking a flight path and it moves, right? Its head won't just be like this the whole time. It might turn its head this way and it'll go like that. And I'm going to show you some cool animations that make it look like we're in a roller coaster. Okay? But it's all about understanding the motion of a point as it moves through the curve. So because of that, we're going to have to understand what curvature is, which is basically something that tells us how curvy a certain path is at a particular point on the curve. And then we're going to learn about something called the TNV vectors, which tells us kind of the motion and the twist that's happening as you move throughout the points on the curve. So it's going to be some cool stuff. Okay. 13.3 is really loaded. So if you look in the textbook, we don't cover all of 13.3, but we cover most of it. If you're a physics major and you're very interested in how this applies even at a deeper level, I encourage you to check that out. Okay, it really goes into depth about that. I think it covers things with torque and all that good stuff, which we won't do in this class. But yes, so that's kind of the layout for today. That's what we're going to do. So let's start with arc length to remind you guys kind of what we did with that. So we're not going to do a warm-up. Let me move this up. Okay, let's see. So section 13.3, we're going to start with arc length. So let me take you back to Calc 2. Recall from Calc 2 that if you're parameterizing a plane curve, x is being parameterized and y is being parameterized, for some plane curve, C, then, let me remind you. So you had x, you had a y, and then you had some curve, C, that was oriented. It's oriented this way. And then you had, at a particular time, right, we're thinking of t as time. Let's say at time A, you're at this point, and at time B, you're at this point. And so your goal was to find the length, excuse the squeakiness, this length right here. How long is the curve from this point to this point? Okay? And so what you did, to remind you here, is you broke up, you said here's t equals A, here's t equals B, and then you broke up this curve into tiny little sections. Okay? If I zoom in on one of these, then what happened was, let's say the path was like that, and you have this point here and this point here, is you use the distance formula to say, look, that small tiny arc length is approximately the distance between those 2 points. Okay? That's kind of how you ended up doing this. So you did that for each of those. You found these distances, which you used by figuring out the change that happened in the x-coordinate and the change that happened in the y-coordinate. So you had the small little change x here, and you had the small little change for y there. Okay? And so then what you did, you had this change delta x and you had this change delta y. And basically you made this little right triangle here like this. And that hypotenuse was the distance between those two points. Okay? So you used a lot of Pythagorean theorem, and you found the Pythagorean theorem, bless you. You found that distance, which then gave you all these little distances that were approximately the arc, little small tiny arc lengths. And then you broke it up into even more pieces, and so on and so on. Eventually, you added up all those tiny little distances, which then gave you the total distance that you had. That was intuition behind how all that happened. And so through this process here, you got that the length of the curve C from t equals A to t equals B, because you were adding an infinite number of sums, you ended up with an integral. And then through the Pythagorean theorem, you ended up with a square root function. But the way you're adding all these little distances here, which ended up giving you the derivative of what's parameterizing x, right? From this, you have that dx dt ended up being f prime. Okay? And that's right here squared. And then you did the same thing, so then you found the change in y with respect to t, and that was g prime, and that was being squared. So all of these represented these small little distances. You added them up from A to B. Question, yeah. Oh, sorry, f of t, f prime of t, thank you. Or some, I think in Calc 2, maybe you wrote dx dt squared, dy dt squared, which is the derivative of the parametric. So then we take all this, and now we bring it up to the 3D dimensions. We do a very similar thing. So for R3, given a space curve C defined by a vector function R of t, where x is parameterized through some function f, y is parameterized through some function g, but now z is parameterized through this function. We're basically going to copy this method. And you're going to have a space curve. But now, if you guys remember the distance formula for in 3 dimensions, it wasn't just the change in x squared plus the change in y squared. What else was involved? The change in z squared. So it's going to look pretty much the same thing because of how we find distances using the distance formula. Okay? So given a space curve C defined by this vector function, where f prime, g prime, and h prime are continuous, the length of C from T to A, T equals A to T equals B, is going to produce a very similar result. But now we're going to add a little bit of more of this vector notation in a little bit. So I do the same thing I did here, this method here, we're going to add all these infinite sums to these small little distances. But now it's going to be the change in x, right? This is the x, this is the y, this is the z. And the change in x with respect to t is just f prime. The change in y with respect to t is g prime, but now the change in z with respect to t is h prime. So it looks very similar because of the distance formula. That looks very similar. But now there's a little bit more life. Let me wait for you guys to see that. What do you guys see any relationship between this expression and the vector function in terms of things you know about vectors?
So length of the vector.
What would happen if the primes weren't there?
Magnitude.
It looks like the magnitude of this, right? But it's not this one, it's the magnitude of the tangent vector, r prime. So now we can also write the arc length as the magnitude of the tangent vector function, which is pretty dope. Okay?
Arc length is the magnitude of what?
The something here, or you say it again?
The arc length is the magnitude of what?
Oh, so notice that we get it, that the arc length is the magnitude of r prime, which we last week defined to be the tangent vector function. It gives you the tangent vector on the curve. What kind of function are we integrating? A vector function or a real value function? Real value function, right? Real value function. So just be careful there. Basically, like a Calc 2 problem. Okay, it's a Calc 2 problem. But on the homework, you're going to have to now integrate functions that have square roots in them. So you're going to have to review some of your integration techniques, trig substitution, factoring things out, all that fun stuff. Okay, so just be careful with that. Just make sure you review integration techniques. Because of now the functions will look a little nastier. So let's try one so we can play with it, kind of see how this is going to work. So this is something you'll see on your homework. It'll say for the curve C given by, let's say the vector function here is 2t, t squared, and 1/3 t cubed. Come on. Find the arc length from t equals 0 to t equals 1. Okay. So this is my f, my h, and my g. So what are we going to have to do to those functions? We have to take the derivative because we got to find r prime, right? So let's do that. So if I take r prime, let's see what that gives me. That's going to give me a 2t, and is that just t squared? That's just t squared. And so then that tells me that if I take the magnitude of this sucker, let's see what that's going to give us. So I'm going to square each of those. Let's see, so let's do 2 squared is 4, this squared is 4t squared, and this squared is t to the 4th. And that's what we're going to have to integrate. Okay. What would you guys do from here, this step? Say it again?
Put it into the integration.
Put that into the integration. Okay, let's do that. So let's put, we're going from what to what?
0 to 1.
0 to 1. This is going to give me the length, which is the magnitude of r prime. And so I'm integrating from 0 to 1 this function here. Let me write it in descending order. T squared plus 4. Okay. Any ideas what we can do in this bad boy? Yeah, Gary. Integrate by parts. That's usually when you have a fraction. Oh, sorry. You're saying I thought you said partial fractions. No. Okay, that's one attempt. Let me hear other ones.
It also looks like 2 plus t squared squared.
So you factored it.
Yeah.
Okay, Jacob? Factoring it. Okay, so is it factored? Can we actually factor it? Let's see. If we can factor it, that's probably the easier way to go. If not, then we might have to do some other, like by parts. What does this factor into? T squared plus 2 squared like that? It does? Sweet. And why is that even super sweet? Yeah, because the square root and the square cancel out. Oh, thank God. Okay. So that makes it hella easier. Now we don't have to deal with the square root. Now we just got this. Right? This guy and this guy cancel off. And so that's actually not that bad. Now we just have to take the antiderivative of that. What's that? 1/3 t cubed. That's 2t. From 0 to 1. So we plug in the ones here. That's going to be 1/3 plus 2. Is that right? And then we plug in 0 minus 0 plus 0. So then that's going to be 7/3. 7/3. There we go.
If you just put it in the calculator during the set.
If you say it one more time.
Can we just put it in the calculator?
Put what into the calculator?
The integration.
This right here? You can to check if your answer is right, but on an exam, you're gonna have to show me how you integrate it.
Oh, okay.
Okay? Yeah. Yes.
For the interval, you need to put a 1
Thank you. Thank you. So, there's this curve, right? That's somehow a space curve. It's moving around, but the length from 0 to t equals 1 second. If we think of this as time, has a small arc length of 7/3. Okay, which is 2 1/3. So, let me see. Hold on, I'm just looking. All right, I'm gonna have to fix my notes. I made a mistake. I integrated wrong. I left this as t plus 2 instead of t squared plus 2. So I'll change it in my notes. Okay, so now I have a kind of higher level question for you guys now. So I'm gonna leave that problem there. So notice the question looks very Calc 2-ish. So now I have this question for you guys that I would like you to discuss with your classmates. So discuss what you think the following represent. So I'm going to write 2 things here. In your own words, try to describe what you think these represent, okay? So I'm going to create this new function. This is still related to this example, okay? I'm just going to write it, and I want you guys to try to interpret it. the folks around you, try in your own words to kind of verbalize what you think these are, what do these represent with this problem that we just did here. Okay, so let's see. I'll have you guys two here chat. Why you guys here can chat? Why you stay? Say it again. I'm just gonna leave it there. Those are good questions. Those are good questions. Yeah. Notice I'm already using the T. Yes. Those are good questions. We'll answer them in a bit. But right now, you guys can you ready? I'll have you two.
I mean, the first thing I thought of when I saw the so then instead of like this, it's going to be like
You guys.
So I can't remember the RU.
I think it's just a double derivative. Yeah.
You don't have to write it down. Yeah, it's more like to get you thinking about it, because it's used a lot in this section. So I don't want to just say it. I want you to think about it.
But if you don't write it down, you get an F. Oh yeah, yeah.
Totally. I mean, if you're the person that likes that writing helps with like process things, yeah. Let me know if you have questions. So it's basically just a magnet question.
So I guess like this area is taking like so then it's just
Well, how is it related?
you know like
Second one?
the second one,
Yeah. Derivative of
what if it was like an integral?
antiderivative of a derivative.
So just
All right, guys, let's see. Just share with me whatever your group said, okay? Whatever your group said. Kenneth, go for it.
We think it's just like the length that has specific time.
Okay. Is it for this one or this one?
The first one.
Okay, so here you said length at a specific time. And when you mean length, do you mean arc length?
Yeah.
Okay. Okay, cool. Anything in your group want to add? Okay, yeah, Gary?
Sorry.
Yeah.
Is T related to the T on the equation over there? The same T?
Like this T here?
Yeah.
It can be.
Oh, okay.
It can be. Yeah, it can be. Can this be t and this be t?
Yes.
No.
No.
You don't want your changing variable to be the same as the input, the bound variable. Okay. Okay, let me see. Let me just hear from some more folks. 7.
We talked more about like how we would kind of like visualize it when we were thinking it out. So we kind of like for the first one we were thinking that it was maybe putting it into terms of a different variable. And for the second one, we were thinking that because the first is the integral of the magnitude of r prime, it would be that just r prime because it's integral. Yeah.
So you're saying when you say it would be, do you mean it equals?
Yes, but in terms of t.
Okay, in terms of t, and then here is it just that? Is that what you mean like this?
The magnitude.
The magnitude. Okay, so you're like the thing that's being integrated, but you're saying now in terms of t.
Yes.
Okay. Kind of using the whole integral and derivative being opposites kind of thing. Okay, cool. And then this, you said you guys were kind of more visualizing
How do you work it out? Yeah.
how it worked out. Okay. All right. Thank you, Dylan.
Number one, I agree with the statement up there that it's the arc length at a specific time. We were wondering at first if there was a use of in there, and he said probably not. It's just an arbitrary time t, but the variable t was already used. And then 2 actually.
Let me just write what you said. U is a arbitrary variable. Okay.
And then actually got a better answer for 2 from the group behind me. Discussed it with them a little bit, which was essentially that since s of t is an arc length, then s prime of t is just the rate of change of the arc length.
Okay, so it's kind of like more of a wordy answer of what this is supposed to give you, right? Okay, so you said, say it again, rate of change of the arc length?
Yep.
The arc length. Oops. So it's kind of like telling us how the length changes. Cool, I like it. Okay. Anything else people want to add? Yeah, no.
Since it's the rate of change of the arc length, it could also be like the speed at which the line goes or object is moving.
Okay, okay. So speed at which I think you said the line moves?
Or object or line.
Object?
Yeah.
Okay. Object moves on the line, right? Okay. Okay, sweet. All right, I'll leave it at that. Thank you. Okay, so let's see. So yes, if we tie back this problem here, do I have it? Yeah, I think I have it graphed in the notes. So let me just see here. The graph ends up looking something like this. So here's X, here's Y, here's Z. And then you have a curve, you actually, that kind of comes in through the back, and it kind of curves, and then it goes up like that. So the curve's doing something like that, okay? At time, if t equals 0, notice that's 0, 0, 0, so it's gonna be the origin, okay? So what we found is here's t equals 0, and then at t equals 1, since the orientation is going like this, let's say this is where t equals 1. Let me write it like that. So what we did is we found this arc length right here, which was 7/3. Okay. So you guys you're right. Yeah. So it is going to give you the arc length of that curve, right? Because I remember I told you tie it back to that example. But let's add a little bit more. It does say a specific time, but starting where though? It still starts at t equals 0. So it's the arc length from 0, except that now this ending time can vary. It doesn't have to be 1 second. So if I plug in t equal 5 into S, now it gives me the arc length from t equals 0 to t equals 5, somewhere over here. So as you vary t, you're gonna get different output values for S of t, which represent the arc length from time 0 to whatever the time is that you input it. Cool? Through this, because you're using t to represent time, you do put what's called a dummy variable into the integral, which could be an arbitrary variable. It just cannot be the same one here. Okay? So you input a particular time, and then the output is the length from time 0 to whatever that time is. That's the output of this new function that we've created. Okay? And so, yes, so imagine I grab this t and I'm just dragging it along here, and then it's giving you all those different arc lengths for each specific t. So then, you guys are right, it does give you the rate of change of how the arc length is changing at a particular time. So if I plug in 5 here, and if t is 5 over here, then immediately, right when I increase that t value, that's going to give me the rate of how fast that arc length is increasing. Okay. And this right here is true because the fundamental theorem of calc part 1. Okay? That if we define a function in this manner, then the derivative of this, the derivative of it ends up equaling the function you are integrating. That's a consequence of part 1's theorem of calc. Okay? So, we're going to be using this function to move us on to the next part, which is curvature. Okay? Questions on these two things? You guys did great. Good job. Yeah.
We said the speed at which the object moves on a line is that.
You can think of it as like the speed at which the arc length is changing. Yeah. But not necessarily the object, but more of the length that it left behind as it's moving. Okay. So what we're going to do now is pretend there's different t values here. And actually, you know what? I believe I have a better visual. Give me 1 second. Let's see. Here it is. Oh, of course, you're doing maintenance on your website. Yay. Okay, never mind. So what we're going to do is we're going to analyze, for example, if I want to know how curvy this curve is at specific points, what we're going to do is, I guess I'll do it like this. Let me zoom in here. Let's say it's like this. You guys see how there's a lot of twist here, but over here there isn't that much twist? What we're going to do is we're going to use the tangent vector to help us figure out how twisty it is. So we're going to get the orientation is going like this. So we're going to get the unit tangent vector and look at it at at different times as it moves through the curve. Okay. Notice that if I find the unit tangent vector at this small little arc here, it's going to twist and change a lot more than here. The unit tangent vector pretty much points in the same direction throughout that process. Okay, so that's how we're going to be able to quantify how curvy something is. It's going to get funky though. Okay, so let's see. Where's my back marker? All right, so let's use this function, which we're going to use in a little bit, to talk about something called curvature. To do that, first we're going to talk about something else that ties into this. Since we're going to end up using derivatives for this tangent vector, we got to remember when a derivative is undefined. So recall that a derivative is undefined. You guys remember from Calc 1? How were you able to look at the graph and determine where a function was the derivative was not defined.
It's discontinuous.
Discontinuous, that was one.
The vertex.
You're giving me like a V shape.
Yeah, like that's a vertex there.
Okay, what was the shape called? Do you remember that?
Absolutely.
How would you describe the graph at the vertex? A V, you're right. Corners. It'd be like a very sharp corner. The derivative does not exist. And there was another thing called a cusp. You guys remember that? It was like a pointy part of the function. So recall that a derivative is undefined if the curve is discontinuous, has a corner at a corner, I should say at a corner. Hold on, let me make sure I'm writing the English right. Recall that a derivative is undefined if the curve is discontinuous. Yeah, I guess at a corner or a cusp. And let me remind you what that looked like. So a cusp. A cusp would look something like this. Some kind of shape like that. This was a cusp. And then a corner looked more like this. Like you guys said, like an absolute value. Okay. And then discontinuity as well.
What about horizontal tangent? Or vertical tangent?
Well, here, remember, it's a space curve. And so we're going to look at the tangent vectors. Yeah, I really wanted to show you this video here, but actually, I have another video. Hold on. I came hella prepared today. I was like, I need hella visuals. Curvature. Yes, yeah, okay. So let me show you what's going to end up happening. Because it's kind of hard to draw. Yeah.
This is also like a straight line with a loop, right? This is like a straight and then.
Oh, kind of like this?
Yeah.
Yes.
Okay.
Yeah. Okay, let me show you guys this real quick. So this is what we're not going to want, okay? So let me show you like this one. Okay, you guys see how this has 4 cusps? There's one here, okay. Look at the unit tangent vector. Look how, you guys see that abrupt change that just happened right there? So let me pause it. Does this happen at 1 second? Hell yeah, okay. So as t is approaching 1 from the left, do you guys see what the unit tangent vector is, like how it's behaving? It's approaching, it seems to be approaching a vector that's going to point towards the left. That's what the limit seems to be doing. But now if I approach t from the right, it seems to be approaching a completely different vector that's now pointing to the right. So the limit will not exist in this case. It's not approaching the same vector. When we were learning limits of vectors, remember that the limit of a vector function was a vector. Okay, so here, because that limit won't exist, we're not going to end up having this base curve being differentiable at t equals 1. Okay, and so at all these cusps, when t is approaching a particular time from the left or from the right, they're completely different vectors. They're not approaching the same limit. Okay. Versus, for example, let's say, let me get a different curve. Let me see, is this at 1 second? Dang it, I wanted it to be. Okay, let's look at 1 second here. As you approach t, as t approaches 1 from the left, it's approaching a vector, this vector right here that seems to be pointing down. Right here, this purple vector, that seems to be what we're approaching. As I approach 1 from the right, it's also approaching that exact same vector with the exact same direction. So it will have a limit there, okay? And so that's why we're gonna want this, it will be differentiable here. We don't have any kind of abrupt changes that happened at cusps and that will also happen at corners, okay? What we're gonna want for the rest of this section are curves that are called smooth curves, where the unit tangent vector changes continuously, smoothly, with nothing that happens like what we saw in the cusps and in the corners. Okay, we're always going to want it to have a vector that the limit approaches, and so it's going to move continuously in what's called smooth throughout this curve, versus something like this guy. Let me see, it's this one. This one still, it doesn't have any cusps or corners. Look, we're gonna go on a roller coaster ride. So it's moving smoothly throughout that curve, the unit tangent vector. There's no abrupt, crazy, discontinuous kind of changes that are happening. Okay? So for the rest of this section, we're gonna wanna look at curves that behave in this way. Cool? Question, Dale? Yeah. No, this one here is where is it? I think it was the second one. This one here will be continuous. It's continuous, it's not detached, it's just not smooth. That's going to be the difference. The smoothness happens with how the unit tangent vector moves throughout the curve. It's continuous here, it's just not differentiable there. And so we're going to use differentiability to describe smoothness. Yeah. Okay. But I just kind of wanted to show you because it's a little hard for me to do here. And show you that whole limit discussion. Okay. So we're gonna define what a smooth curve is. So we're gonna say a curve given by a vector function r is smooth if its derivative, which is the tangent vector, is continuous. The tangent vector moves continuously. That's what that means. It's not saying r is continuous, which then would mean that the curve is not detached. It's not talking about detachment and discontinuity. It's saying that r prime is continuous, so that the tangent vector moves continuously. Okay, and we don't want the tangent vector to be the zero vector. So this is the mathy definition, but in essence, it's saying you don't want your tangent vector to not move, and you don't want your tangent vector to you want it to move continuously. Question is a question.
Don't want it to be.
I said it, I didn't write it, sorry. Yeah, you don't want it to be zero vector. Okay. I'll apologize in advance. It's about to get heavy lecture right now. Okay, so I'll try to give you guys some energy through some dancing or something. Okay, so I wrote a bunch of stuff here that I'm already saying, but basically in the notes, I'm just reminding you, we're going to define curvature by how that unit tangent vector moves. Okay, but let me do it over here since I'm going to erase it. But what we're going to do, I want to look at my unit tangent vector and how it moves, but in relationship to the arc that I'm looking at. That means in relationship to the arc, the arc length that I'm considering. Okay? That's where it's gonna get funky. So let me give you the definitions to show you what I mean. So this is how we're gonna start by defining curvature. We're gonna say for a curve C given by a vector function R, its curvature, which we're gonna call K, defined at T is given by, so if I want to find the curvature at a specific time, it's going to be the rate of how the capital T is what we call the unit tangent vector, which we defined last week. I'll do it again, okay? The rate of how the unit tangent vector changes with respect to S, which is this S, the arc length, okay? But this is going to give me a vector, so I want the magnitude because I want a number to tell me how curved it'll be.
So it's T.
Say it again.
What's T?
Oh, yes. Where, and this is just what we covered this is what we presented last week, where this is just R prime divided by its magnitude. It was the tangent vector, but the unit tangent vector. Huh?
And S is.
And S is the rate of how this arc length is changing from a fixed point to any time that we're considering. Okay. Let's write some English here.
So DS is like.
Change in how the unit tangent vector change in hold on, I didn't write the English file. I was gonna say changing how the unit vector changes, but that sounds kind of funny. Change in how let's say moves visually here. It's tracking how the direction of how the unit tangent vector is moving with respect to the arc length S. Okay? That's what it's giving you here.
So S is like just the outline. Yes.
S prime is this,
Magnitude.
the magnitude of R prime. It's a little overwhelming right now because a lot of stuff it's kind of colliding all together. Okay, so that's why I'm trying to keep it separate. S, and this is why I couldn't just say it. I needed you guys to think about it. S is the arc length from a particular time to some particular some fixed time to a varied time t. Okay, so ds is telling you the change in that arc length. Okay. But not with respect to time because it's just ds right now. It's just a change in the arc length. Okay. So let's say I had a straight line and I look at the arc lengths here. And I look at, let's say I fix this arc, I fix this arc here from here, and then this is my unit tangent vector. And then I do it here, and then this is my unit tangent vector. How much did the direction of the unit tangent vector change?
So
Was there any change? There was no change whatsoever. So then what do you think this is going to give you? It's going to give you 0 because there was absolutely no change. Okay? What does that mean? That means since there's no change, your unit tangent vector, as it moves throughout the curve, is pointing in the same direction. So what is that going to tell you about your curve? It's a straight line. Exactly. Okay? Versus if there is change, then that's going to give me a positive number because this is magnitude. So the bigger the positive number, what do you think that means? The curvier the curve. That's right. The curvier the curve. Curvier the curve. Now, this formula doesn't use R at all. It's not using R. So what we need to do now is figure out how to bring R into the picture. Okay? Because otherwise it's too hard to compute this with the way it's defined. So I want you guys to notice notice we have t here. I'm going to write it again. T is r prime of t. T of t here is r prime of t divided by the magnitude. And s of t is what we define to be this integral for any vector function given by r, which represented the arc length for this specific curve given by this r, which from fundamental theorem of calc part 1 says that s prime is going to be equal to the integrand function here. So I'm like summarizing the discussion, okay? Because we're going to use that now here. We're looking at the rate of change of how t is changing with respect to s, but s actually depends on t. So there's a composition happening, right? There's a composition happening. This is telling me t and how it changes with respect to s, but then s is affected by little t. So there's a composition happening here. I want to figure out this rate, but I want to somehow bring in t into the picture. Okay? So what did we use to find rates of change with compositions? Chain rule. Chain rule came into the picture. Okay? So let's consider the rate, sorry, not the rate, the change in t of s. When I write this, I'm thinking of t as a function of s. Okay? And the change of s, which we defined to be a function of t. Okay? From the chain rule, we know that the change, if I want to find the change in capital T with respect to S, the chain rule says multiply the rate of change of T with respect to S, and then multiply that with the change of S with respect to T. Okay? That's what the chain rule is going to tell me. And let me stop right here. I had it right. Okay. I want to figure out the rate of change of t with respect to the very most independent variable at t here. I multiply the rate of change of these two times these two. Okay? Questions so far? It's heavy with theory. I'm sure your question will be like 3 other people's questions. Jacob.
Isn't the table for scenario 3 terms? Products being added.
Added, that would be product rule when you're adding the primes. But with chain rule, like, let me just take you back to Calc 1 to remind you. Hold on. Yeah. So if I let, I'm trying to like super fast make an example here. Okay. Let's say, G is a function that gives you the number of products. So at a particular time, it tells you how many products were produced at a company. Okay? And let's say F tells you how many products you've made, and then it'll tell you the cost needed to produce those products. Okay? What's confusing is that we do this. Like in Calc 1, that's how you've been doing it. And so you've been thinking, which is not wrong, okay, which is not wrong. It's just you've been using the same variable for both of these functions. And I think that's the part that's probably like making it a little fuzzy here. But in the real world, or what's really happening, if we get it at units, you're thinking of the output of G that's being plugged into F to give you some other quantity, right? So in reality, if I bring this back to T here, and you take the derivative of this, you've been doing F prime of G of T times G of T. Right, that's kind of like how you've been doing it. But if I use rate notation, what you're really doing is you're saying, how is the cost changing with respect to time? As time is changing, how is my cost changing? Well, this tells you the change in C with respect to how P is changing, the products, times the change in the products with respect to time. Okay, this is more of the algebra that you guys learned in Calc 1, but this is more of how it's actually applied in real world application with rates. Okay, this gives you the rate of the products and how it changes with respect to the G function, G, which is giving you the products. So it's telling us how the cost changes with respect to products times how the number of products change with respect to time. That's kind of what chain rule does with rates of change. Okay? So that's how it's being applied here. Okay? Okay. So I'm looking for this bad boy, which is right here. So we're going to divide both sides by this rate. Okay? So then this implies that the change in T with respect to S is going to be equal to how capital T changes with respect to little t, divided by how S changes with respect to little t. I divide both sides. Okay? So therefore, the change is going to be the change in capital T with respect to little t, which is T prime of little t now, over the change in S with respect to little t, which is S prime little t. Cool? What is S prime of little t equal to then? It's equal to the magnitude of R prime. So then this equals T prime of t with over R prime of little t. So that now is, I can use that because now T uses R. I can find capital T, get this ugly vector function, and then take its derivative to give me T prime. and then its magnitude of it. So now this solely depends on R now. Now I can actually figure out the curvature using this R function. Okay? So what we end up getting is this 3 little dots here, and math means therefore. Your curvature, we can find it by taking the magnitude of this bad boy here. Okay? So because I have to take the magnitude of this, and this is already just a scalar, so I have to just take the magnitude of t prime. So it ends up being the magnitude of t prime over the magnitude of r prime. And then this is the one that's more useful that we can end up utilizing R with now. Question, yeah.
Can you explain again how you got that?
How do I got this right here?
Yeah.
Okay, yeah, I'll go on here. So, I think who asked me? One of you guys asked me like, when will we use all these rules? Remember, sometimes we write all these rules. Here's an example of this. So you guys learned that if I take the magnitude of a vector times a scalar, it was the absolute value of the scalar times the magnitude of the vector, right? You guys remember that rule that you learned? The bottom is a scalar because it's a magnitude. So I factor it out. The absolute value of a magnitude is just still the magnitude since it's still positive. So think of it like this. Right? Think of this guy here. There's a lot of steps there. Hold on, maybe that's why you're asking this question. So this is like, think of it like this. Think of it like that. This t is the vector, and me dividing it just means I'm multiplying it by the scalar 1 over it. Okay, so this is like my c, and this is like my v. So then I use this rule, I take the absolute value of this, which is still just itself because it's positive, times scalar multiplication times the magnitude of t. So I end up with this. Yeah. Through this property. And then again, I can think of this magnitude times 1 over this as just this magnitude divided by it. Okay? Yep, no.
So is that the same as saying over the magnitude of r prime squared? Because t prime is over r prime magnitude, right?
Careful. T is over r prime. But not, this is t prime, so I can't use that and substitute it in there. I get what you're trying to do. Question, yeah.
Can you take the derivative of that and substitute it?
Can I take the derivative of this and substitute? Yes, you can. Yeah. Which still will just give you this and maybe look a little different. Yeah. Okay, I'm gonna have you guys try one and then we'll take a break. I want you guys to use this here to find the curvature of the following two curves. You do not have to completely redo this. This is just the theory of how we get this formula. Okay? It's just the theory of how we ended up with that formula for curvature. So find a curvature k of t for the curves. And then there's b of t equaling, I'm gonna make it a 2D, a two-dimensional curve. 2 cosine t, 2 sine t. And then this other one is t, 2t plus 2. Yeah, so try this one first. Find the curvature function for it. And then find the curvature function for this one. Using the formula that we just derived. Okay? And of course, just work along with your classmates. There's going to be a lot of derivatives that you're going to have to do. Say it again? Oh, correct. Actually, let me do that to make it less complicated. Thank you. This is R. It's R, guys. It's R. But let's just stick with it so there's so much stuff flowing around, so it doesn't become confusing. There we go. Thank you. Right? It does, yeah, because there's just so many variables flying around. This looks gnarly in itself. So yeah, you gotta be careful, keep track of what you're doing. Remember, this is t. You gotta find t first. Do all this to find t. Then once you find t, then you take the derivative. And then you take the magnitude of that at the end. There's a lot to keep track of. So just be as organized as you can. Technically, it should be a function of t.
I got 1/2.
And then for the second,
So,
Careful, careful. Careful with this one, guys. Be organized. I believe in you.
Professor, so
Yes.
we actually have to calculate, the length of T1.
Yes, you do. You do. Let's go. How did you get? What's the magnitude? Pretty much. How did you do that?
Because here is our prime.
Oh, you gotta be careful. So this would be 4 sine
right
squared,
now, I just found
4 cosine squared. You factor the 4 here.
Or at least it's a lot easier.
Think about it, because you have to Yeah. So it'd just be 1 over.
See, he knows the value. He knows trade, he knows the trade value. He knows.
I'll do it. Yeah, right? Yes.
Now, this is normally a function of t. Sorry.
It just like draws the graph for you.
The same thing that I did in the first one. When I got to,
As your point moves,
final t, into the magnitude.
does the curvature change? So for every t, what do you think it means? It's always turning the same.
It's a point.
Remember, like,
One and two.
I got 0.
I didn't change anything. That's good.
Well, maybe you just mean that the curve is squared or something like that, then you're gonna get KLT as like a function.
All right, guys, you can check your work. I'm just gonna write some of the stuff here. So you should have got your T to be negative cosine T, negative sine T. It's just because
angle is.
But I know.
Yeah.
One over it.
Oops, sorry.
Yeah.
Yeah, just zero.
I love that. Yeah, it's just, because the T goes away.
Yeah.
If there's a square that'd be a different story, but you know, not. And then the magnitude is.
I like writing cosine.
Oh, yeah, that's right.
Okay, guys, question, Thomas.
I'm not really too sure how you got the, I'm not, could you go through how you got that T?
This one?
Yeah, because,
It's T prime.
oh, it's T prime?
It's T prime, it's T prime.
Oh.
Yeah, these are the T primes, and then these are the magnitudes of R prime.
Okay, gotcha, sorry about that.
Is that cool? With this one? Okay.
I just didn't see the prime there, my bad.
Oh, it's all good, bro. Okay. So normally, not normally, but this is a function of T. And what ended up happening is we don't end up with the variable T, it kind of went away. So you ended up with a constant function. Okay. What does this tell you about if you're moving along the curve and how curvy it is? What does this tell you? Jacob.
Curvature is on the same, so the line is the curvature along the entire curve is exact.
It's going to twist the same way and in the same direction all throughout the curve. So if the tangent vector, let's say is changing in this direction all the time, what do you think the curve should look like?
Circle.
It's going to end up being a circle. And notice, if x equals 2 cosine t, and y equals sine of t, what is that parameterizing in the R2 plane? What is it? It's going to be a circle of radius 2. Yeah, so what this actually is, the curve of C is a circle of radius 2. Okay? And we don't have to go, the text goes a little bit deeper into this, which is what we don't have time. But in general, when you have a circle of radius r, you can prove this yourself the way you did this. What do you think the curvature will be? It's going to be 1 over r. 1 over r. Yeah. You can do that. Just let r, you could do the same thing you did here, but just let this be r. And you'll see everything cancels off to just 1 over r. Okay, so in general, for a circle of radius r, the curvature is constant, and it's just going to be 1 over r. What happens as r goes towards 0? What is the curvature approaching? It's approaching infinity, right? As r goes to 0, the curvature is going to infinity. And what does that mean? Is that a smaller circle has more twist the smaller it gets. It's more curvy. Okay? Like if I'm walking on a circle, it's kind of weird. If I'm walking on a circle, I'm walking on a big circle, like let's say I take a straight path on our planet. If I walk from here to here in 1 second, it feels pretty straight. But if I was walking in a tiny circle, within 1 second, I'm like, yoop! I twisted a lot, right, within that 1 second. So that's kind of what this is mathematically showing you, if that's the case. As r approaches infinity, what happens to the curvature? It's approaching 0, which means the curvature is getting really straight. The curve is getting really straight. So the bigger the circle, the more the straight it seems like you're walking. Okay? Which is weird. If you guys try to picture like an infinite circle, it just keeps getting bigger and bigger and bigger. Okay? For this one, you end up with a curvature of 0 for every t value. So that means that the unit tangent vector at every t just keeps pointing in the same direction regardless of where you're at. So what does that tell you about the curve? It should be straight, right? And so what I want you guys to notice, here x is equal to t and y is equal to 2t plus 2. So see how you guys can substitute the x in here for t? That's just the equation 2x plus 2, the linear equation 2x plus 2. Okay? And so yes, it is indeed a line with slope 2/1 that crosses at the y-intercept 2. So it's this line right here. Okay? So that's what math is saying. It's like you have all these math objects and it helps you really study behavior of things mathematically. Okay? Okay, let's take a break. I'm gonna do what you guys suggested. I have hella homework. So I'm gonna go down, I'm gonna split it up, just look through the stack here, pass back, collect your homework. I believe I have homework sets from last week. Yeah, so that would be 5 and 6. So just pass through your homework. Hopefully your homework was stapled. If not, just look through it. Making you guys do the work now. Oh no, I did pause it. Okay. All right, guys. Is homework still being passed around? It's coming. All right. Here, let me just take it back, and then I'll just.
We'll end up for you.
We'll just do it later. Let's just do it later. Okay. Otherwise, you're gonna be distracted. Today's a doozy. Wow, there's still more. Okay. There's a lot of homework. Okay, guys. So, this was an easy problem because so many things canceled, right? Especially because the magnitude of r was a number. Some of the homework problems, the magnitude here will be some ugly square root function. And so as you can imagine, this is going to get really tedious and very annoying, basically, okay? So there's another formula for curvature, which is proven in your textbook, that looks nastier, but it's actually easier to implement when you're doing it, okay? This is a theorem. So we're going to have different formulas for curvature, okay? So the first part of this theorem says for a vector function r of t, a different way to find curvature trust me, I know it looks nastier, but it'll be easier, is the magnitude of the cross product, which already sounds scary because cross product is gross, with r prime and r double prime, divided by the magnitude of r prime cubed. The magnitude to get to. And I know, it looks gross. You guys will see on the homework, it's actually it's easier to end up using. Question, take it. Well, you will use you start off by using the curvature function that you guys just used here, and from that you can derive that. And that's basically what the textbook ends up using. Okay? All right, the other part is, like these examples that you guys did, if you're dealing with two-dimension curve, on R2, if you have y as a function of x, like you guys did in Calc 1, its graph is given by a vector function. But here, instead of x, we're going to use t, where x is parameterized by x. Okay? What do you think y will be? What function can we use for y in terms of x? F of x. So if I think of my graph parameterized through this vector function, through the first part of this theorem, you can derive a different formula that's now in terms of f only. Okay? The curvature is, here it's a function of x, is the absolute value of f double prime of x over 1 plus f prime squared, and all of this is raised to the 3/2. I know it looks a little gnarly here, but this is derived using the property from the top. So these are helpful formulas that you'll want to use in your home. Okay? Question?
Is that f of x or f prime of x?
This is f
On the
prime.
bottom, sorry.
This is f prime of x. F prime of x. And these will be very useful in your homework. Let me make sure everything we copied was correct. Yeah, Charlie.
For curvature, it's curvature of the entire curve. We don't have to change every single segment.
Good question. So on the homework, they're going to ask you find the curvature function. Like it'll just say find the curvature. So it'll be kind of like this, except that you might end up with an actual function of t. These both ended up being scalar functions, but on the homework it won't. That might not happen. There will be functions of t.
So depending on the time,
The curvature is different, exactly. Other homework problems will say find the curvature of a function at t equals blank. So then you'll find the curvature function and then plug in t to give you the value. Okay. And so this is it for curvature. Okay.
So those formulas give us the same thing as the one we just learned.
Yep. If you guys use this to find the curvature through this, it'll also give you 1/2. It's just a different way of doing it. But here, what gets hard is, as you guys saw, you have to take a derivative of a derivative of a derivative, right? Where here, you just do these two derivatives separately. Like you just find r and r prime, and then you're done with derivatives. Then you just do cross product and magnitude. You guys see how that's a little easier? I mean, the cross product is never fun, but it's not as bad. Okay. Oh, I forgot, there was one more thing I wanted to say. This is not in the notes, actually, so I just thought of something right now. Something that the textbook does, which doesn't really explain, is how can I turn this vector function into a three-dimensional vector function so that it's still parameterizing the same curve? Where? To which coordinate? Z. If I just change this so it looks like this, now I can do the cross product. Because cross product was only defined for three-dimensional vectors. So if your vector function is not three-dimensional, and you're like, oh crap, how can I take the cross product? Just make it three-dimensional by letting z be 0. Okay? Why will that work? Because on the xy plane, I have a curve that's behaving like this, I can think of it in 3D as the same curve, but now it's on the XY plane. And then it just has a Z coordinate of 0, so it stays on the XY plane. So the curvature that happens on this curve is the exact same curvature that will happen to this. Okay? Jacob, yeah.
Wouldn't it be a surface?
If I put a 0 here,
Oh, yeah, sorry, 0.
it'll still be the curve, remember. It'll still be a curve, a space curve now. It's just that the space curve stays on the XY plane. Yeah? I just wanted to add that comment, have it in the video for future reference.
So you
Yep,
can't,
yep.
if it was 2D, you can't just do like a indeterminate?
If it's 2D, you can't because cross product was only defined for 3-dimensional vectors. Yeah. You'll see it too as you're working it out. If you only have 2D, you'll see the formula of cross product needs a third component.
I guess like in my head, I'm thinking like, oh, if it's not like a 3x3 matrix, it's a 2x2, and then if it's 2x2, then you just run that determinant. But I guess it just doesn't translate like that.
It won't. Yeah, it won't. Okay. Yeah, because if you take the determinant route, you're gonna need this guy.
Yeah.
You're gonna need that column. If you take the formula route, the formula had all this stuff like this, but it had a third component. The way we defined it the first time, cross product. Okay. All right, guys. So now, oh, here I had a little video. So now, we're done with curvature. This is the end of the curvature discussion. Yeah. Now I want to talk about this T and B thing, but let me show you guys. Just sign me out. Give me 1 second. Sorry, a little video I had signed me out. Where are you? Here you are. Okay. All right, let me see. Chapter 13. All right, so we just did curvature. Here's the theorem, by the way, of that formula. It goes a little bit here. Let me go to the T and B. Hold on. Okay. Okay, so now what we're going to do is we're going to focus not just on the direction that you're moving with and how the tangent vector is changing, but also how you twist as you move along that curve. Okay, so we're going to create 3 vectors. One we already did, which is a unit tangent vector. Okay, that one we already know how to do. And then we're going to create an orthogonal vector n, where n will be perpendicular to capital T. Okay? And then we'll use those 2 orthogonal vectors, take the cross product to create this third vector B. Okay? And what that's going to do, it's going to help us understand how you move throughout a curve. Oops. The tangent vector is the purple one, n is going to be the orange one, and B is going to be the blue one. Okay? It's a little small. There we go. So notice T is pointing in the direction that you're moving. If you're on a roller coaster, the purple vector tells you the direction of your eyesight. What do you guys notice about the orange vector? It seems to be pointing towards the center, right? The orange vector, you guys see that? Okay, let's look at another one. Oh shit, where'd it go? Is it coming? Oh, there it is. Whoa, you see that? That's it twisting. So that's what this is going to help us do. Now we're going to get more information. Right, now we're going to get, let's go on a roller coaster here. What do you notice about the orange vector? Keep an eye on the orange vector. Okay, it's all good, it's all good, it's all good. Let me see one more. So yes, so this is used a lot in like when it comes to motion, where you really care about the twisting effect of the path of the object. Seems to be kind of pointing like towards the center-ish of things, but okay. So yeah, so this is used a lot in things that require motion where there's twisting involved. Okay, and in the direction of which the twist is going to happen. I'm guessing, I don't see it here, but I'm guessing it's probably used in like animation as well. You want to mathematically code all that motion. Okay. Okay, so that's what we're going to do. Is we're going to figure out how to find this. Okay. All right. So as you guys noticed in the picture, finding B was just the cross product of those two vectors, right? So the real task is, this is T prime, but if I have T, how do I find something that will always be orthogonal to T? Yeah, that's going to be the challenge here. Because I can't do cross product to find that vector. So I'm going to have to construct something. Let's see. So normal and binormal vectors. So before we jump into finding these vectors, we're going to have to figure out a property that helps me figure out a orthogonal vector given a vector. Given a vector, how can I find something that will be orthogonal? Sure. Okay. So there's going to be a property we're going to use to begin. Consider the following property. So exciting. Right now, the class is going to feel like upper division in class. Super stuff. Okay, so here's a property that we're going to use. It says, if a vector function R has constant magnitude, then R and its derivative are orthogonal. What does that mean? That means its position vector will always be orthogonal to its tangent vector. That's what that means. As long as the vector function R has constant magnitude. Okay, so if I'm at the origin, that means that my position vector always has the same magnitude, no matter the time. Right? Which is really weird. What does that mean? What does that tell me that it should be orthogonal to the tangent? So let's prove it. We have the tools here to prove that. So in math, this is what's called an if-then statement. If this is true, then this is true. And so the way you prove an if-then statement is you assume the first condition. You assume this to be true. So let's assume that we have a vector function that has constant magnitude. Then your task is to then prove the consequence of that, of the statement. Okay? So thankfully, I don't have to prove the beginning. It's just, I'm going to assume. So let R be a vector function so that, how do you think we're going to write constant magnitude in that? How would I write that? Well, magnitude, right? Let's take the magnitude. C equals some constant, always, right? Will equal C for all t and scalar c. Meaning for every t, no matter the time, the magnitude always just equals that scalar. So it'll have constant magnitude. Okay? All right. So usually when you're doing these proofs, these if-then proofs, you just start out with the initial condition. And now it's your task, and this is why proving is so cool. Okay? It's your task to be creative on how you're going to conclude this. So the way Noah does it can be very different how Dylan does it. Okay? So normally what you do is in the class, you're like, okay, you gotta review your notes, and you gotta be like, okay, what properties do I know that use magnitude? And I'm also thinking orthogonal. How can I show these two things are orthogonal? Mathematically, how do we show that? Dot product 0. So if I can somehow show that the dot product of these two things is 0, then I can conclude they're orthogonal. So then you look at your notes and you got to say, okay, what do I know? What properties do I know about magnitude of vectors that somehow use dot products? Does anyone remember any of those? A property that uses dot product with magnitude?
Cosine.
There's the cosine one. There's a cosine one. But for the cosine one, I have to take the dot product of two different vectors, right? That would be involved. There's another one. Scalar projection.
That has a dot product on the
Correct. So that's one too. For that one, this is the hard part of proofs, okay? Is that there's so many things that you've learned by then, you got to figure out which one to use. So it's kind of like you're going to get lost in the woods and you have to find your way out. Okay? Jacob, yeah.
I think it's like A dot B equals magnitude of A times magnitude of B times.
That sounds like what Noah was saying, but I think the way you said it with sign would be the cross product. The magnitude of the cross product is the one that uses sign. Okay, so I'm just showing you like how, like the type of thinking you'll need to do for stuff like that. Okay, there's another property that said if I take the dot product of a vector with itself, you guys remember what that's supposed to equal? The magnitude of itself squared. Right? So that one uses dot product with magnitude as well. The magnitude of itself squared. But what is the magnitude always? With our assumption? It's constant. So then, by my assumption, right, we have that this dot product will just equal that c squared. Okay? Any idea now what we can do to bring in our R prime? We can't do the same thing because we don't know anything about the magnitude of R prime. We just know about the magnitude of R.
Just translate into R times time R of one.
Somehow, somewhere we want that to happen.
So you just get to substitute and that's good.
Like you're saying bring this into the picture here somehow? Correct, yeah, somewhere we want to do that, but somehow we want to do it from here. Now, let's take the derivative of both sides. Because remember, what is the dot product? what happens when you take the dot product of a vector function with another vector function? What kind of function do you end up with? Is it a vector function or is it a real value function? A real value function like the ones you guys did in Calc 1, right? So then I'm going to take the derivative with respect to t to both sides. Okay? And then here you gotta go, oh crap, was there a rule that told me about the dot product of the derivative of a dot product? No, it was a little more complicated. There was a rule that you guys learned about taking the derivative of a dot product of two functions. Eventually, somewhere we'll, yeah. Product rule with dot products. And so that's what you gotta go to your notes and look at like rules now. So that's, yeah. So I'm giving you guys, I'm showing you how this would work, okay? So yes, there was the product rule that said r prime dotted with r, the derivative of one function dotted with the other function, plus the first function dotted with the derivative of the second function. So that's the left-hand side because of the product. What is the derivative on the right-hand side of a constant? With respect to t? Zero. It's a fat zero, right? Because it's not changing with respect to t. It's just always constant.
We already know about it because constants are prior to zero.
Well, we have that this sum is equal to zero. But what do you know about the dot product of two vectors if you swap them? It's commutative. So I can swap these, bloop, and then it's just this guy now, right? So I'm adding this guy twice. So I end up with 2r dotted with r prime. So then finally divide by 2. And what does this give me now? If I divide by 2, I get that r dotted with r prime is equal to 0. And so what does that tell you? They're orthogonal. There's a dot product of them. So then I ran out of space, but remember at the end of a proof, there's a little box. Okay. Okay. Questions? Yeah, Jacob. Well, I'm also not going to have you guys prove on tests and stuff like that. We'll see. Maybe a bonus. I might throw something like that, but I don't like testing on proofs because I'm not teaching. I'm not training you on proof techniques. I would feel bad testing them because there's all kinds of proof. This is called a direct proof, where you directly prove it. Like just grind it out. Assume the first thing and then prove the second thing. There's different kinds of proofs called proofs by contradiction, proofs by contrapositive. Like there's all kinds of proof techniques. That's what I'm going to teach in the class next spring. Okay, but we're going to use this. Okay, we're going to use this property. So recall that T, what kind of vector is it? What's the name of it? Unit tangent vector. So it's a unit vector is defined to be a unit vector, which means that the magnitude of it, the magnitude of t of little t, is always going to be equal to 1. And so therefore, I have a vector function with constant magnitude. So what does this property tell me? That its derivative is orthogonal to it. Okay? And so from the property we proved, we have that T and T prime are orthogonal. Say it again? This one? Oh, say it again, David. Oh, yes. Yeah, it's a vector. Now, just because T is a unit vector, it doesn't guarantee T prime is a unit vector, okay? Just because T is a unit vector doesn't tell me that the changing rate vector is also going to be orthogonal. That one's a little funky to kind of like conclude, but it's not going to be. We can't assume that, okay? But what we're going to do is we're going to define. Let me just write definition here. That's how we're going to use T prime to make these three vectors that we were supposed to make that I was showing you. So for a space curve given by R of T, we're going to define the unit normal vector to be n What was the relationship between n and t that you guys saw on the little video here? They were perpendicular to one another. So what we're going to do is we're going to use t prime because we know it'll be orthogonal to t. And so just divide by its magnitude, and then I'll get an orthogonal unit vector. So it's going to be defined to be t prime of t divided by the magnitude of t, so that it's a unit vector. Since the direction of this unit vector is the same direction as t prime, it'll be perpendicular to t. Can I nerd out just a little bit more? Okay, so in upper division class, you're learning all this stuff, and then the homework problem will say, prove these two vectors are orthogonal. Okay, so when you guys learn proof techniques, there's something called the lemma. Okay, it's just weird names. I know, it's all kinds of weird names. So what you do is you say, okay, there's this big result that I want to prove, but it seems like I have to prove something before that to give me what I want. And that's what's called a lemma. So you prove what's called a lemma. This is the lemma. I had to prove this thing first to then give me what I actually wanted to prove to begin with. Okay? I'm just showing you because when I transferred, there was all these words I'd never heard just being thrown around. Okay? So a lemma is something you prove, like a smaller property that you have to prove to help you prove your original problem that you're looking for. Okay? And it's spelled like this. Lemma. So you'll hear that word, lemma. Okay? Okay. That was just a little side note. All right. So now that we know how to find t, right? You guys just did it on this problem here. We know how to find t. And now we know how to find n, so then we just take the cross product. So the unit binormal vector is defined to be b of t. And be careful here, the order matters. It's t is the left vector, cross n. That's the right vector. Hold on. Binormal. That's the name of it. Binormal. I'm guessing it means like it's like perpendicular to two different things, which it is. It's perpendicular to n and it's perpendicular to t. Because as usually in this class, normal kind of means perpendicular to something. So binormal, it's perpendicular to both of those. Yeah. And actually, guys, leave some room here. All right, let me write this a little bit lower. It's the same thing. I'm just going to move it down. Unit binormal. It's the cross product of t and n. Okay? So it's clear that this vector has to be a unit vector because we're dividing by the magnitude of the vector on top, right? But how do we know that if I do a cross product of this vector, which is also a unit vector, cross with another unit vector, how can I guarantee that that's also a unit? Well, that's right. So let's see, how the heck do I guarantee, what theorem did you guys learn to find the magnitude of the cross product? It's the sine one. But what is it? Well, what is it equal to?
Magnitude of t times magnitude of n times sine.
Sine of the angle between these two vectors, right? What's the angle between these two vectors? 90 degrees. What is the magnitude of t? What is the magnitude of n?
1.
What is sine of 90? Bam. Math, baby. Just kidding. Okay? So it's indeed a unit vector. And so here, let's associate a little picture to your notes. To kind of make sense of what's happening here. Okay. So in your notes, let's just draw a curve. Okay. And let's pick two different points on the curve. Let's say it's this one, and then let's say it's this one. Okay. And let's say it's oriented in this manner, like this. Okay. T, the tangent vector, the unit tangent vector. I'm going to draw it. How are we going to draw it? Which way is it pointing? Towards the right or towards the left? Towards the right, because of the orientation, right? It points in the direction that you're moving, and it has to be tangent. So it'll look something like this. Okay? And as it moves, same thing here, it's tangent, and so it should point towards the right. Okay? Because n is defined to be the change of t, what ends up happening with n is that it points in the direction in which t is curving, which is changing. So if this vector, is it changing this way or is it changing going up?
Use right hand rule.
We'll get there, yeah, we'll get there. But this next part for n is important. So as the point moves, is the tangent vector moving up or moving down this way? It's going to move up. And so n is going to point orthogonal, perpendicularly in the direction that it's moving, that it's changing. So it's going to point this way. Okay. Okay. And then notice here, for this one, which direction is the tangent vector changing? Is it going up or twisting down? Down. So then the tangent and the unit normal vector is going to face down this time. That's why you guys saw that flip that was happening. Okay? It points, and I'm going to write all this stuff out. It's going to point in the direction in which you're turning, that you're twisting. Okay? Okay, so now we know these two are perpendicular to each other. Now, as Yong Yang mentioned, we're going to use the right-hand rule to determine which direction B is at. Okay? Which one's my index finger? T. T, the one on the left. T, and then N. Okay? So I got T and then N. So is the binormal vector pointing out of the board or into the board? It'll point out of the board. So it's gonna, I can't really draw that, but it's gonna point this way. Okay, outside, out. Up. Here, T, N, the binormal vector is pointing into the board. It's pointing like into the board. Which is hard to see, I know. But all these three are orthogonal to each other. Sorry, perpendicular to one another. Okay? And so that's why you guys saw that frame doing stuff like this. We're not going to go into this, but then the section goes deeper into this, and then it talks about the twist that's happening. That's where all that torque and stuff comes in, okay? We're not going to study that torque, okay? Yeah, that's where it gets deeper. If you're a physics major and you're like, yo, this is my jam, look into it, okay?
So where the normal is changing, that has to do with the concavity, right?
There's a relationship with concavity and curvature, and you can see it here. Because the second derivative has to do with concavity for plane curves. Yes, there is a relationship. Okay, so I just have some remarks, and then that's it for today. So let's do a little summary here. So T, which is defined to be R prime divided by the magnitude of R prime, gives you the direction of motion. Sorry. So it's going to tell you which way you're moving. N, which is defined to be T prime of T over the magnitude of T prime, points in the direction you're turning. B is the cross product of these two vectors here. And then we have that T, N, and B are all orthogonal. If you read more into this section, there's a plane that contains both N and T. And its normal vector of that plane is B. And so what it's studying is as you move throughout that curve, it's telling you how that plane is turning because it's turning according to B. So that's a little bit more that the section goes, but we'll stop there. I used to cover it.
T and B are orthogonal to each other.
Are orthogonal to each other. Thank you. To each other. Yes. And we'll end it with that.
So for problem set 4, we covered this. And the question 2, I see there's a table there. That was for our last to describe something.
Problem set 4 has a question from this section and from what we're going to do on Thursday.
Oh, we are going to do the first one.
Correct, we're not there, yeah. The second question has to do with Thursday's section. Okay? Yeah. All right, guys, that's it, we're done. Finished early.